So my name is Beth Puzio, and this is my presentation about my poster, which I've entitled Continuous Variable Distributed Quantum Sensing in Integrated Photonics. So I'm based at the University of Bristol, and at Bristol we do a lot of work in quantum photonics. And quantum photonics is one of the most important platforms for quantum technologies because it offers quite literally light-speed communication, low decoherence rates, and can fairly easily be incorporated into pre-existing classical setups. So typically when experiments are done in quantum photonics, they're done in bulk optics. And by bulk optics, I mean we're using mirrors and beam splitters. And bulk optic setups can typically take up an entire optics table, such as this setup shown here. But at the University of Bristol, thanks to recent advances in nanofabrication technology, we do a lot of work in integrated photonics. And by integrated photonics, I mean that we can incorporate an optical setup such as this one in bulk optics into a tiny little silicon, sorry, I messed the pictures up there, into a tiny little silicon photonic chip such as this one here. And for scale, this is on the size of about millimeters. So clearly, integrated photonics offers a really great platform for efficiently scaling up quantum technologies. And one such application is in quantum sensing. And in quantum sensing, we try to sense certain parameters with a precision that surpasses the limits that are imposed by classical physics. So say, for example, we could have some biological sample of which we want to measure the refractive index. We could use classical light to probe this sample, and we could measure the phase shift of light at the output. And if we wanted to measure this phase shift to a certain degree of precision, we'd have to probe the sample with a certain light intensity. And unfortunately, this could mean that the sample ends up being damaged because it's sensitive to light intensity. What we could do instead is then probe the sample using quantum states of light. And if we were to use quantum states of light, we could achieve that same degree of precision with which we measure the phase shift, but using a lower light intensity, and therefore the sample is preserved and isn't damaged. So it could be more beneficial to us to probe the sample in multiple different locations. Let's say if we wanted to measure the average refractive index across the sample. What we could do then is we could entangle our quantum probe states, and this would allow us to measure this function of our parameters with a precision that surpasses the precision we would achieve if we were just using separable states of light. So therefore, by utilizing entanglement, some function of parameters can be measured to a certain degree of precision with a lower light intensity than it would take to measure to the same degree of precision using separable states. And this is what we would call a distributed quantum sensing scheme. So in my experiment, I'm implementing a distributed quantum sensing scheme onto a silicon photonic chip. And in this experiment, I have 4 integrated phase shifters, of which I'm going to be measuring the average of. Now, I'm going to be conducting this experiment in the continuous variables regime. And by continuous variables, I mean that I'm using squeeze light as my probe, as opposed to just using single photons, which is what we would call the discrete variable regime. And the advantage of doing an experiment like this in the continuous variable regime is that we can generate our entanglement deterministically just by using squeeze light and linear optics. So this is a schematic of my experiment that I have on my silicon photonic chip. And as you can see to the left, I input squeeze vacuum at that input port on the left. And with this set of 3 cascaded Mach-Zehnder interferometers, I can split my squeeze light across the 4 modes and generate entanglement deterministically across the 4 modes. Then the other advantage of doing this experiment in the continuous variable regime is that our entanglement is fairly robust to loss. So even with a certain level of loss on each of these modes, I can still retain some degree of entanglement and therefore perform an entanglement-enhanced measurement. Then on each of the modes, I'm using integrated homodyne detectors to perform the measurements of the phase shift on each mode, and then I can measure the average of these phase shifters with an entanglement-enhanced precision. So what's the relevance of this experiment and what's next? And I should have actually included these pictures on the previous slide, but you can see from these pictures that's what the silicon photonic chip looks like. So this experiment, because of the integrated linear optics networks for entanglement generation and the arrays of integrated detectors, this experiment explores the potential for on-chip CV entanglement generation, detection, and utilization. For example, this experiment explores the potential for continuous variable cluster state generation on chip, which is really beneficial for continuous variable quantum computing. Yeah, that's my presentation. Thank you for listening.
So over the last decade, we've made tremendous progress building better quantum computers with more qubits and less error from noise. But what is it that we're actually going to use these machines for once fault tolerance is achieved? So currently, the most promising application for quantum computing is to make advancements in chemistry. And this alone will have enormous consequences for society. So advancing chemistry means that we can increase the rate at which we're able to discover new drugs and bring them to market and cure diseases. It means that we'll be able to find better processes to design new materials, and this could lead to the development of more energy-efficient solar cells. This is possible because, as chemists, we already rely on computer models to help us understand the incredibly complex nature of the molecular world. And quantum computers will give us exponentially more power to run these computer models. So the question then is, how is it that chemists are going to use quantum computers to help them with their research? So as a chemist, the way that we solve a problem about a chemical system is that we try to answer two categories of problems. Those relating to the static properties of the system and those relating to the dynamic properties of the system. And it turns out that classical computers actually do a really good job at solving these static problems, but they're really bad at solving these dynamic problems. So an example of a static problem would be, what is the ground state energy of a molecule? And an example of a dynamic problem would be, how fast or at what rate does a chemical reaction occur? And so because classical computers are so good at solving these static problems, initially researchers also thought that quantum computers would also be good at solving these static problems as well. And as a result, the majority of research into finding applications for chemistry and quantum computing has been focused on developing these static methods. But what I found with my research is that actually the reverse is true. Quantum computers are much better at solving these dynamic problems, and chemists need to start thinking about how they can utilize this to make advances in their research in the future. So having realized this, we created a quantum toolkit of algorithms designed to solve exactly these types of dynamic problems. And I'm going to quick tell you about one potential example and how this toolkit works. So one area of chemistry that our toolkit shows a lot of promise for is photochemistry. So photochemistry is the area of chemistry where you have a source of light, like the sun. The sun provides additional energy that allows chemical reactions to occur that wouldn't occur otherwise. One very famous example of this is the photochemical reaction by which chlorofluorocarbons like freon react with ozone and pull ozone out of the ozone layer, leading to depletion. Our toolkit is ideal for solving problems in photochemistry because the kinds of problems you want to solve here are all dynamic in nature. So in this example, what you'd want to know is how quickly does a compound react with ozone, and when it does react, how much ozone is it going to pull out of the atmosphere? These are all examples of dynamic problems. So we think that our toolkit could quickly and accurately answer these kinds of questions without approximation, and this could allow scientists to better predict and reduce the amount of harmful chemicals that humans emit into the atmosphere in the future. So how exactly does our toolkit solve dynamic problems in chemistry? So one of the strengths to our advantage, or one of the advantages to our approach, is that it follows the same steps that a chemist performs in a laboratory setting to analyze a chemical reaction. So we start off in a lab, we prepare the molecules that will participate in the reaction. We allow them to interact with one another, and as time goes on, they form product. And then after enough product has formed, we perform some type of experiment to read out the properties of the product that we're interested in. So our toolkit actually works the exact same way. So the first thing that we do is we prepare a representation of the reactants that we're interested in on the quantum computer. Next, we run a type of algorithm on the quantum processing unit, or QPU, called Hamiltonian simulation. This allows the reaction to take place. And then finally, we read out the properties of the reactant that we're interested in. And so if you have any questions about the details of how this works, please come find me during the poster presentation, and I'd be happy to talk with you more about it. So we expect that within the small molecule regime, so this consists of molecules on the order of 10 or so atoms, that our toolkit will be implementable on a relatively small-scale fault-tolerant quantum device consisting of hundreds to thousands of logical qubits. And we think that this could possibly be the earliest application to achieve quantum advantage in chemistry using our toolkit.
Thanks, Bernie, and hello, everyone. Diamond is a unique material, marveled for its strength, beauty, and perfection for centuries. But apparently, when diamond is imperfect, it shines even brighter. The nitrogen vacancy center, or the NV center in short, is a defect in diamond. It has a vacancy, or a missing carbon atom, next to an impurity nitrogen atom in the diamond lattice. And thanks to NV centers, breakthrough quantum technologies that can operate at room temperature are already here. These include quantum computers that do not have to live inside refrigerators to keep their qubits alive, and single spin-based quantum magnetometers that can go extremely close to samples and do very high-resolution scans and measurements. And even lasers that can be controlled by tiny changes in magnetic fields. And this list goes on. The way an NV center operates in all these amazing applications seems to have one feature in common. And that is, it takes in a high-frequency beam of light as an input. This is typically green light, as you can see in these pictures, and it emits red light as an output. And that's why our NV center glows in pink. And the brightness of this pink glow depends on its quantum spin state. Now, one of the major challenges that we face in all these kinds of quantum technologies is fighting noise and making these desired output signals stand out at the tiniest of length scales. But thankfully, there seems to be a clever way to tackle this. To understand that, let's first look at two roles of the NV center, first as a magnetometer and then as a spin qubit. What you see at the top left of the slide is the typical line shape that we would measure when using the NV center as a quantum magnetometer, or for magnetic field measurement in simple terms. And the plot below that is a typical spin qubit readout signal for the NV center. We can greatly amplify and engineer signals like these by coupling our NV center to what's called plasmonic particles. Now, these are a very special type of particles that can control light at scales 10,000 times narrower than a strand of human hair. And this is typically the regime where the conventional approaches to controlling light, like microcavities, for example, fail. And in our recent work, we predicted the possibility of enhancing the brightness, depth, and the contrast of NV signals, like the ones you see on the left-hand side, by orders of magnitude, by coupling our NV center to plasmonic particles, as you can see in the right-hand side plots. However, these enhancements only occur in precisely tuned parameter regions. So if you're aiming for such huge gains, it's absolutely essential that you model and fine-tune your system first before heading off for any experimentation or device design. And we've derived a verified theoretical framework that could perhaps help you with this. So our theory can currently help you to enhance the NV center as a magnetometer and as a spin qubit, as we just saw. And we aim to extend this to capture all capabilities of the NV center, ranging from measuring electric fields or electrometry, all the way to controlling nuclear qubits in diamond. And what you see on the right-hand side of the slide is a snapshot of NV-based quantum technologies that are currently being experimented in different labs around the world. And as you can see from the little green boxes there, some of these technologies are already in the spotlight for commercialization. Plasmonic engineering enabled by our framework and its extensions could help to push the fundamental limits of all these technologies, ranging from measuring activity in cells all the way to controlling qubits in room temperature quantum computers. So in summary, the future is looking pretty bright for diamond quantum technologies. But they'll shine even brighter if we cleverly combine them with Plasmonics. Thank you very much.
Thanks very much. So my name's Lewis, and today I'll be pitching to you a project with Peter Brown and Roger Kolbeck on generating maximum device-independent randomness. So first up, I would like to just motivate to you why we're interested in randomness in the first place, and if we want to do any sort of cryptography, such as quantum key distribution, a necessary resource is for both parties to have access to a perfect random number generator. Now, what do I actually mean by a perfect random number generator? Well, firstly, if I'm using this generator, I shouldn't have any power to guess the probabilities of its outcome, so it should look random. Great, but we actually need a stronger notion which considers a third party, and this third party could be, for example, the manufacturer who gave to us this device, or it could be some adversary who's trying to hack into our generator, and we need it to look private to them too. So this is a stronger notion called private randomness, and we need to be able to certify this. And well, quantum theory gives us a solution. So for example, if I was to send a single photon into a polarizing beam splitter, and I follow the quantum mechanics, I know that both detectors should click with probability of half, and this is my random number generator, which is great. But now, instead, imagine this device is given to you by a manufacturer, and you now have one of two options. You can either trust when the manufacturer tells you this is a random number generator. You can actually trust that they're telling you the truth. It's questionable whether you would want to do this. Or you can open up your device, and you can go through every component and check that it matches what the manufacturer says it does. And this is an incredibly challenging task, and is ultimately undecidable. So you can never hope to go through every component and perfectly characterize your experimental setup. You'll inevitably miss something, and this leaves open security loopholes. So what we'd ideally like to do is certify our randomness based purely on measurable statistics. And that's where Bell's theorem comes in and enables what's called device-independent random number generation. So the setting is as follows. We consider two devices, A and B. Their inputs, X is given to A and Y is given to B, need to be chosen randomly themselves. These devices can't communicate to each other. And then what Bell's theorem tells us is that if we estimate this probability distribution, so over many rounds we can estimate the probability of outcome A and B, given the input X and Y. If we can estimate this distribution and see that it violates a Bell inequality, well then these outputs A and B should contain some randomness. And now what do I mean by a Bell inequality? So this Bell inequality is a linear function of this observed probability distribution. So how does this process then work? So after many, many rounds, Alice and Bob, they sample X and Y, they record A and B, they estimate this probability distribution, they calculate what's called the Bell value from it, and they check if this is above a certain threshold. And if it is, we have what's called a Bell violation, and we can certify some randomness. And the really important thing to point out is that in no point in this whole process do we need to know the physics that goes on in these devices A and B. This is purely, we're concluding private randomness purely based off an observable quantity without any device assumptions. So what's our research focused on? So I said that we need to violate a Bell inequality, but I didn't tell you which Bell inequality to violate. And the space of quantum correlations is an incredibly complex mathematical object, and well, it's incredibly difficult to isolate which Bell inequalities are actually good for this task of certifying randomness. So the first thing that we do is we provide a generic technique that gives you back a Bell inequality, which will certify the theoretical maximum amount of randomness per interaction with your devices. And now, secondly, I said that we need to violate a Bell inequality to give you some randomness. And this implies that the correlations we're using are in some way non-classical. So there's no classical description for what's going on in these devices. But one can ask the question, given more non-classicality, and this is defined in some meaningful way, does this always give me back more randomness? So if my system is more quantum, do I get back more randomness? And the answer is not always, and in some cases, being more non-local or more non-classical, we can actually certify less randomness than the other case. So what we do is we actually provide some quantitative trade-off for this observation. So how does this bring us back to our original objective? Well, if we know how to certify more randomness per interaction with our devices, we can ultimately design more efficient random number generators. And now violating a Bell inequality is extremely demanding, so if we can make these things as efficient as possible, this is very advantageous. So with that, I thank you for your attention.
As quantum information systems grow in both scale and complexity, distributing entanglement, that is, entangling objects that are far apart from each other, is becoming increasingly important. It's my view, and we heard this morning from Steph Simmons as well, that quantum networks will help us achieve a number of key milestones on the way to utility in both quantum sensing and computing. I really liked that analogy that the network is, in fact, the computer. To do this, though, we need to develop quantum interfaces, which are devices that can speak to many kinds of quantum device. I'm investigating a candidate spin qubit, which can be addressed, controlled, and read out with light. These single atom qubits could be the basis of a network that shares information in entanglement using single telecom photons over fibers which are kept at room temperature. Connecting quantum computers together is hard. Current demonstrations of connecting microwave-based quantum computers together rely on these bespoke cryogenic setups. And that's because they're connecting together microwave quantum computers using single microwave photons. I envision a system that looks a little bit more like the cartoon we have on the right, in which a fiber link that is tens of kilometers rather than maybe tens of meters long is used to connect devices that are in fridges that are anywhere between a few meters and a few kilometers apart. It's also worth me saying here that this kind of technology could be used to connect qubits within one fridge, qubits within one chip, or across many chips in a multi-chip module, and so on and so forth. The technology that we're using for this, the hardware platform that we're using, is ions of erbium that have been doped into crystals. Erbium has compelling properties as a light matter interface with an optical transition very close to or in the telecom band, the telecom C band that is, which is the lowest loss band that we have. It also has these spin state transitions that you can tune with a very modest magnetic field, a small magnetic field to be right in tune with the same frequencies that superconducting quantum computers use. On the right here, you see some really compelling results from the Thomson group in Princeton, where they used a single erbium ion to generate indistinguishable photons and conduct an HOM, a Hongo-Mandel experiment, over 36 kilometers of fiber. I think that's a record. The link itself is all at room temperature. The ions and the crystal are the only thing that are in the fridge. There is a catch to erbium, though, and that is that the transitions are very slow. This is because erbium has a very low dipole moment, and so you don't get very many photons per second out of these atoms. They're very pure, very indistinguishable, they look really good, but you don't get that many, maybe hundreds per second, rather than millions or billions per second as you get out of some other emitters. So that's exactly what my work is on, is engineering stronger dipoles for erbium atoms, and hence faster optical transitions. And we're doing this in a really interesting way. We're engineering the nanoscopic environment around the erbium atom to speed up its transition. We're using this quite friendly material system, calcium fluoride, which is a crystal that you can grow in not super exotic conditions, about 1100 degrees Celsius, as a test bed for this investigation. The reason for that is that there's a number of different ways that erbium can live inside a calcium fluoride lattice. There's a charge compensation that has to happen. Calcium's a 2+, erbium's a 3+ for the nerds in the room. And so the charge can be compensated in a number of different ways, and we can see each of these lines, as you can see in the middle plot here, we can see each of these lines spectrally distinct from each other. The other thing that we can do is preferentially create some of these sites by annealing our crystals at relatively modest temperatures as well, about 700 or 800 degrees Celsius, for 8 or so hours. In that annealing process, we can create this oxygen-compensated site, which is the orange highlighted site that you can see there, in preference to the kind of default sites that you see in the crystal lattice. Something that's really nice about that oxygen is that it enhances the dipole moment of our erbium atom, speeds up its optical transitions, and means that you get more photons out of it. So what we do in our lab is spectroscopy on these crystals. We're measuring lifetimes, line widths, spin properties, coherence times. And in fact, right now in the lab, as we speak, we're running experiments for the physicists. We're running Hahn and Rabi type experiments in the optical to measure the coherence times and oscillator strengths of these, basically to measure this dipole moment of the erbium atom in a small magnetic field in a magnet that we made ourselves. So far, we've used these results, as you can see from the lifetime measurements there are at the right, to confirm that the presence of an oxygen does dramatically reduce the lifetime of our erbium atom. But this really is just scratching the surface of what we're doing. The next few steps for us are coupling these erbium sites to photonic cavities that have been fabricated in the calcium fluoride host, or possibly to photonic cavities that have been fabricated in another crystal. The other thing that's worth me saying, given I've still got 55 seconds left, is that I don't necessarily think that this is a be-all and end-all material, but this is a really, really nice playground for us to find out what it is that makes erbium sing properly for us. You know, what can we do, what can we make in our nanoscopic environment around the atom to really get it to be the best emitter that it can be, the best erbium atom it can be. In the long term, I envision making designer sites like these, either in a dielectric crystal like calcium fluoride, or possibly on the surface of a piece of silicon photonics with precision-placed donors. Maybe some other atoms are directly placed, flanked either side of the erbium atom to really speed up that transition.
So actually, firstly, I'm going to say how fantastic it is to see so many people at the posters having a conversation over lunch. That's the whole reason why we sponsor this activity. And the talent, not just the talent that's on display here, but everyone who's actually contributed and put forward their video submissions, I really appreciate them. And in actual fact, being on stage right now in itself is an achievement because there were quite a number of submissions that actually went in, so thank you all for doing that work. There's no other drum roll. In second place, I'm very happy to award second place to Harini. Elliot is the person who's in first place.